This is Dr. Wood with Citadel Civil Engineering. This is Civil 203 Dynamics, Learning Objective 2.4.3, in which we are going to discuss polar motion kinematic equations. So when we think about polar motion, what we're looking at now is another orthogonal coordinate system that relates to polar coordinates. So maybe you remember polar coordinates from a math class. This is in chapter 11.5b of your Beer-Johnson textbook. We're still within particle kinematics. But the idea of polar motion is that we have some angle, some rotation, and then some distance from the origin, like so. And so when we think about the radial direction, again, we're going to use a unit vector, E sub r, that always points away from the origin. Okay, so E sub r is going to point away from the origin. That's our unit vector for the radial direction. And in the transverse direction, that's going to be perpendicular to that. E sub theta is just going to be perpendicular to the radial. So this is where we capture our rotation around an origin, perpendicular to radial. Now, this notation is going to be really actually fairly cumbersome for us to do. It's very math heavy, but we're going to use this idea a lot when we start looking at rigid body. So it'll simplify a fair amount, but it's a thing to keep in mind. So the first thing that we want to think about when we look at our radial unit vectors is that we're going to have our r, and then we're going to do a time derivative with respect to that distance from the origin. And so we would have an R, and your book and the FE reference handbook use this notation of R dot, and that's equal to dr dt. So maybe you remember it as a prime or a dot. The two different mathematicians, Newton and honestly, I forget right now the other guy. The other guy used that dot notation, and so that's the notation we use here. And then the second derivative with respect to time, like so. And so we're going to do these time derivatives with respect to time. Now, when we look at the transverse direction, we're going to have the same thing. We're going to have theta, so how far we've rotated, and we're going to have theta dot, the derivative of theta with respect to time, and theta double dot, the second derivative of theta with respect to time. And so this is going to end up relating to something we'll talk about a lot in rigid body kinematic properties, which is going to be theta, which is our angular position, omega, so that's like a W with the curly tails wrapped in. And let me go ahead and close this slide. I think we've got what we need from it. So, okay. So omega, the tails curled in, that's our angular velocity, and alpha, which is our angular acceleration. So this is looking at our rotation about the origin. And later we're going to learn that this relationship between theta, omega, and alpha, or theta, theta dot, and theta double dot, is actually the same relationships that we can describe for rectilinear motion. And so we can have an angular acceleration as a function of position, velocity, or time, and then we can use those equations just like we had before in rectilinear motion. So we're going to get a lot of use out of those rectilinear motion equations. And so this is all dealing with rotation. So a little bit of foreshadowing, we're going to use the theta dot, and the theta double dot. Now, if you look in your FE reference handbook on page 77, you will find the following equations for polar kinematic properties. So first, we're going to recognize that our position vector is always equal to r times the radial direction. Now, we would say that's not terribly helpful because that radial direction is just pointing away, and we need that theta to keep track of the direction. But this does technically take care of it. It points away from it, so that radial direction. And then we're going to have the velocity. So remember, we're going to do dr dt, but we have to keep those vectors in mind. So if you want the derivation, you'd go check out 11.5b. It's not just a straight up r dot and a theta dot. Instead, we're going to have r dot in the radial direction and r times theta dot in the transverse direction. Okay? And so when we do that, our units are still going to work out to be meters per second or feet per second or whatever, whatever system of units we're working for velocity. But we're going to have both a radial and a transverse component. When we think about the acceleration, it gets even more complicated. The equations become even nastier. So we're going to have r double dot, like so, minus r theta dot squared in the radial direction, plus r, plus in the transverse direction, r theta double dot plus 2 r dot theta dot in the transverse direction. Let me double check for my notes that I got that all right. We can also check with our units to make sure it works out. Yes, that looks good. All right, so that's what we've got going there. So these are nasty looking equations, but it turns out our process isn't all that bad. We're going to start with a kinematic property diagram. And I'll admit that generating a working mental model for polar coordinate systems is very challenging for me. We would only really want to use polar when we have our parameters in r and theta. Otherwise, path coordinate system's probably going to be our better bet. So we're going to have our kinematic property diagram like that. Then we'll be able to do our time derivatives. So we'll go through and we'll calculate r dot, r double dot, theta, theta, theta double dot. And then we can write our kinematic relationship equations in polar. That's these guys up here by substituting in the r dot, and r double dot, theta, theta dot, and theta double dot. And then hopefully at that point, we can solve. So I look forward to working an example problem with you. There's the full set of notes for polar motion kinematic relationships and equations. And I'll work an example problem with you in class. See you then.